UC, and I would like to welcome you all to the Wonders of Physics show. This is actually a great event for all of us, and this is the first time that Wonders of Physics show moves to the Middle East or to Africa. And the presenter today is Professor Brent Sprunt of the University of Wisconsin, who has presented this Wonders of Physics show hundreds of times in the United States, and has attracted many young students from all over the United States. And we would like to welcome you to the Wonders of Physics show, and I would like to welcome Professor Brent Sprunt. I would like to welcome Professor Clint Sprunt. Oh, there he is.
Welcome to the Wonders of Physics. I'm sorry.
But I just came from my other job as a magician. You know, there's a lot of similarity between physics and magic. Both physicists and magicians do interesting demonstrations. But today we're not going to do magic, but sometimes magic comes in handy in physics. In fact, just the other day I went to the hardware store and I asked for a 1 meter long piece of rope. And they said, well, we don't have a 1 meter long piece of rope, but we have these two little short pieces. And I said, well, that's no problem, because I'm a magician, and any magician can change two short pieces of rope into one long piece. Actually, I didn't do that at all, I just made that up. But I did go to the hardware store and I asked for a piece of rope, and they said, well, would you like the kind of rope that has 2 ends on one end and 2 ends on the other end? Or maybe you'd like the kind that has 2 ends on one end and 1 end on the other end. And I said, no, I just want the regular kind of rope, the kind where when you tie a knot in the middle, you have a rope with 3 knots in it. But like I said, today we're going to do physics, not magic. And the first demonstration requires a very brave volunteer. Who would like to help? Someone? Okay, come down here. Come around here. What is your name?
Holly.
Holly? Holly? Are you a good at sports?
Yes.
Oh, good. Have you ever gone bowling?
No.
Oh, you don't know bowling. Well, a bowling ball is a very...
I know the bowling like this and...
That's right. Are you good at that?
No.
Not very good. Well, you know, you don't have to be very good for what we're going to ask you to do. What we'd like you to do is go over to my assistant, Ahmed, and he will show you what to do. Right here. We're going to take a bowling ball that has a mass of about 6 kilograms, and it's suspended from a wire from the ceiling up above. And we're going to make what we call a pendulum. Now, what we'd like you to do is to hold that right about at, let's move you a little far forward. That's about it. Now hold that right by your head. Can you hold it? Good and close? Okay. Hold it there. Now when I tell you, I want you to let go. Are you ready?
What?
Let go. Put your hands down by your side and don't move. Once more. Give him a hand. Thank you. Now, the reason we could do that is one of the most important principles in all of science. It's called the conservation of energy. The bowling ball had a certain amount of potential energy when it was up above its lowest position. And when he released it, that potential energy changed into kinetic energy, the energy of motion. And the bowling ball went out, gained potential energy, lost kinetic energy. When it came back with almost exactly the same amount of energy it started with. And that's because of this very important law of the conservation of energy. We can change energy from one form to another, but we can never create it or destroy it. So that's why we knew that we could do that safely. Now, another principle of physics that involves the physics of motion has to do with rockets. Do you recognize this? That's right, it's a fire extinguisher. It has carbon dioxide inside. And when I press down right here, some of the carbon dioxide gas shoots out. Now, this demonstrates so-called Newton's third law of motion, the law of action and reaction. When the carbon dioxide goes that way, that exerts a force on the fire extinguisher in the opposite direction. And I can illustrate that by sitting on this rotating stool, and I'll turn on the fire extinguisher. You see, it makes me go around. And so that's Newton's third law, action and reaction. Now, you've probably seen that. You may have seen in the Olympics sometimes, you see ice skaters go out on the ice, and they will begin to spin around, and they'll put their hands over their heads, and they will spin really fast. And that's another principle of the physics of motion that we call the conservation of angular momentum. So if Ahmed would give me a spin right here, I'm going to start with these heavy weights out at arm's length. He's going to spin me around rather gently. Rather gently, hey. When I bring the weights in, I spin quite fast. And then I can make myself go slow or fast. And this is because when I bring these in, I decrease my moment of inertia, and I increase my velocity as a result. Now, another demonstration that involves inertia is this thing right here. It's a beaker of water. Who thinks I can take this tablecloth and pull it out from under the beaker without spilling the water? You think I can do that? Well, some people say yes and some say no. Let's try it. Do it faster? Well, I don't know. Well, that's right. That's because the beaker has a property that we call inertia. That is the tendency of an object to remain at rest if it's initially at rest. So if I pull the tablecloth quickly, the force I exert on it is of such a short duration that it doesn't move the beaker very much. Now, here's another very interesting demonstration. Do some of you ride a bicycle? A lot of people, but you may not have seen a bicycle wheel you can hold in your hand. And this is a very special bicycle wheel because I can sit on the rotating platform with it. I'm going to have Ahmed, my assistant, spin it up to a very high speed by pulling on this string. And you notice not much happens unless I tip it. When I tip it one way, it makes me go around one direction. When I tip it the other way, it makes me go around the other direction. So I can make myself go either way. Now, some of you may have ridden a bicycle without holding onto the handlebars. Have you done that? It's not very safe, but it illustrates a principle of physics. If you want to turn to the right, you just lean to the right. You see, it makes me turn. If you want to turn to the left, you lean to the left, and it makes you turn to the left. And that, again, is because of this property of the conservation of angular momentum. Now, while I have this, I can demonstrate another property, and that's so-called gyroscopic action. I can suspend this by one end, and you see it doesn't fall as you might expect it to. And that, again, has to do with the conservation of angular momentum. I can do it by the other end. I'll just hold it with my hand. And you see there, too, it doesn't fall. But if I stop it, then, of course, it does just as you would expect. So that's the principle of the gyroscope. Now, I want to ask you another question. I have in one hand a ball actually it's a wadded up piece of tissue paper. In the other hand is a coin, 1 Egyptian pound, I think. If I drop them side by side at the same instant, which do you think will hit the ground first? Who thinks this will hit the ground first? Who thinks the coin will hit the ground first? Who thinks they will hit the ground at exactly the same time? Well, that's good. There are people that think all three things. But you know, in physics, we don't just vote, we actually do the experiment. So let's try it. And those of you who thought the coin would hit the ground first were correct, but maybe not for the reason you thought. Not because it's heavier, but because they both have air resistance. And the resistance that the air caused on the piece of tissue paper was greater than the air resistance on the coin. And that's what caused the coin to fall faster. Now I can illustrate that with this apparatus right here. Don't know how well you can see this, but in here is another coin and a ball of cotton. And there's air inside this tube, so not surprisingly, when I turn it upside down, the coin falls faster than the cotton. Now you may not be able to see the coin from the back of the room, but you can probably hear it. And you can see the coin hits the bottom well before the cotton does. Now the reason I'm doing this inside of this glass tube is so that we can remove all the air and eliminate the air resistance. To do that, we use this vacuum pump over here, and we'll have Ahmed turn on the vacuum pump and remove the air. Now it's impossible to remove every bit of air. That would be a perfect vacuum. Fortunately, we don't need to do that. We'll get most of the air out. And once we have done that, we can then close this valve down here. Is it down far enough? We can close that valve. After the valve is closed, we no longer need the vacuum pump, so we can disconnect it. And we have a tube with what in it? What is in here? Cotton? Coin? Anything else? Nothing? Air? A vacuum? Actually, those are all good answers. There is some air in here, not very much. It is what we call a partial vacuum. But it's good enough, I hope, that when I turn it upside down, you can see how rapidly the cotton now falls, right beside the coin. And to show you that there's no trick, I can let the air in. See the air go in, and I can turn it upside down one last time, and you see the cotton falls much slower. Now, while we're talking about air, I have another demonstration here that involves air pressure, and for this I need another volunteer, someone who is very strong. Okay, you look pretty strong. Come on down here. Come around over here. And I'm going to take two hemispheres. They're called Magdeburg hemispheres, after a little town over in Germany called Magdeburg, Germany. And many, many years ago, there was a politician. He was actually the mayor of the city of Magdeburg, who was an amateur scientist. And he would amuse the townsfolks by taking two hemispheres, somewhat bigger than these, and placing them together like this, and removing all the air from the inside. Now, what is your name?
Marwan.
Marwan? Okay, Marwan, you think you're pretty strong, huh? Well, what we're going to do is remove all the air from the inside here, and then we're going to see if we can pull them apart. Now, when Otto von Guericke did this, he had two teams of horses pulling half-meter diameter hemispheres apart, and they were not able to do it. And that's because of the large pressure of the air. But here we have a miniature version of that demonstration. So now we've removed most of the air. Should be able to close the valve and remove the hose. And let's see if we can pull this apart. Okay. You are strong. Now, keep pulling, not too hard, because I'm going to let the air in. Thank you. And on every square centimeter of area, there is a weight equivalent to about 1 kilogram of atmosphere weighing down on it. So there's about 100 square centimeters there, so it's something like 100 kilograms of weight pushing those hemispheres together. So it's very, very hard to pull them apart. Now I have here another demonstration that involves air pressure. In here I have a very small balloon that has been blown up with a little bit of air, and it's been sealed off. And it's inside of this jar. And right now there's air in this jar. Now I'm going to ask you a question. What do you think would happen to the balloon if we remove the air from this jar? Who thinks the balloon would get smaller? Who thinks it will get bigger? Who thinks it will stay the same size? Who thinks it will pop? Who has no idea? Well, there's a lot of answers of all types. And of course, in science, we don't just vote. That's not how we determine truth. But we will perform the experiment. We'll remove the air from this jar, and we will see what happens to the balloon. Okay. So we connect it to our vacuum pump. Have to make a good tight seal. And keep the balloon from covering the hole where we're removing the air. Otherwise, we can't get the air out. So let's try again. Well, those who thought the balloon would get larger were in fact correct. And the size of a balloon is determined by a number of factors. It's determined by the pressure inside the balloon. Well, we didn't change that because it was sealed off. It's determined by the elasticity of the balloon pressing in, but it's also determined by the pressure of the air outside the balloon. And when we remove that pressure, then the inside pressure is relatively larger then, and it causes the balloon to expand. Now, what do you think will happen when we let air in? It'll get smaller. That's a good guess. Let's try it. So it went back to its original size. And that again illustrates the pressure that air exerts. Now I want to show you another demonstration that requires a very brave volunteer. Who would help? Someone very brave. Okay, come down here. You have to come around. Okay. Oh, you do look brave. What's your name?
Mohammed.
Mohammed?
How are you?
I'm very good, Mohammed. So you're brave.
Yeah.
Would you like to lie on our bed of nails?
Okay.
Now, wait a minute. Over here, we have a bed that contains 1,000 very sharp nails. You're still brave. Okay. Now, we're going to lower the nails so you can comfortably lie down on your back. Then we will raise the 1,000 nails, trying not to put 1,000 holes in his back. Okay. Let's lower the nails. Thank you, Mohammed. Okay. Maybe you've been on some uncomfortable beds before. I don't think you'd want to sleep all night on that, but it's safe to do that because there's so many nails. So no matter how much he weighs, the amount of force on each nail is relatively small because his weight was distributed among hundreds, if not as many as 1,000 different nails. So each nail was pushing on him with a relatively small force, small enough not to do him any particular harm. Now, showing you things about pressure and gases, I want to show you another gas that is called liquid nitrogen. And guess we don't have, can we put a little liquid nitrogen in here so I can just show people? Normally nitrogen is a gas. In fact, the air that you're breathing right now contains about 80% nitrogen and about 20% oxygen. The oxygen, of course, is what allows you to live and breathe. But air is mostly nitrogen. Now, normally nitrogen is a gas, but if you cool it sufficiently, it becomes a liquid. Just like steam becomes a liquid if you cool it sufficiently. But you have to cool nitrogen to a temperature of 196 degrees below 0 Celsius for it to liquefy, or a mere 77 degrees above the absolute coldest that anything can possibly be. When you cool it that much, it becomes a liquid. And do we have a little bit of liquid in there? I don't need very much, because I just want to show you. It's a liquid that looks a little like water. In fact, I can pour it. It's a clear liquid, but it doesn't make things wet. And that's because when it comes in contact with the table, it right away warms up and it boils. And you can tell something's happening. It's still boiling. But when it boils, unlike steam, which is very hot, when this boils, it is still very cold. It's at very low temperature. And when it cools the air, the water vapor in the air condenses into tiny droplets of liquid water. And that, in fact, is what makes a cloud. Now, with liquid nitrogen, there are many interesting things we can do. Sometimes we put things in the liquid nitrogen and show how brittle they become. Of course, it's very dangerous to let the liquid nitrogen touch your skin because it will instantly frostbite you. However, there is something I can do. I can just pour it over my hand, and it does me no harm, and that's because of something called the Leidenfrost effect. And you're probably actually all familiar with that. If you go home and put a pan on your stove and bring it to a very high temperature and then put a few little drops of water in it, you may have noticed that the water doesn't instantly boil. It forms little drops that dance around. You may have seen that happen. And that's because the water does begin to boil, and it forms a layer of steam between the droplet of water and the hot pan, and that steam forms an insulated layer that keeps the water from boiling. And the same thing happens with my hand. When I pour it over my hand, there's a thin layer of liquid, nitrogen gas that forms between the liquid and my hand that insulates my hand. However, I can only do it briefly, and if I were to cut my hand and put it in there, that would be very dangerous. So I'll not do that. Now, there are many interesting things we can do with liquid nitrogen. And the next thing I want to do uses this long pipe that is sealed on one end and hollow on the other end, and we're going to fill it with liquid nitrogen. So if Ahmed will just put some liquid nitrogen in here. Meanwhile, I'm going to put on these gloves to protect my hand. And I have here a cork, an ordinary rubber cork stopper like you would have in a bottle. And so I'm going to put on these gloves so I can safely touch the pipe without freezing my hand. And once we have it filled with liquid nitrogen, now you notice as we fill it, what looks like, you may call this steam, but it's not steam, and it's not smoke. Steam, of course, is water vapor, and in fact steam is invisible, you can't see it. And it's not smoke. Smoke are tiny particles that you get from the combustion of something. But what you're seeing is actually liquid water that is from the water vapor in the air that condenses when the cold gas comes off from the boiling of the nitrogen inside this pipe. So we don't need to fill it completely all the way, but we'll get a good bit of liquid nitrogen in there. And then I'm going to take this cork, and I'm going to simply pound it on. And then I'm going to take the whole thing, which is quite cold. Oh my goodness. They blew the cork off and they went way back to the back of the room somewhere. And that's because when a liquid changes into a gas, it expands. In fact, liquid nitrogen expands by a factor of about 700 when it changes from a liquid to a gas. So a little bit of liquid makes an enormous amount of gas. But of course, all that gas couldn't fit in here. So instead, what happens is that the pressure built up to a very, very high value and reached the point where it blew the cork off. So there are many interesting things one can do with a substance as cold as liquid nitrogen. Now, while we're talking about gases, I have a couple of balloons here that have gases in them. What do you think is in this balloon? Helium? Why do you think it's helium? Because it's floating. It's less dense than air. It's lighter than air. It rises. But you know there are other gases that would do that? Do you know an example of another gas that's less dense than air? Hydrogen. How could we tell whether that balloon had hydrogen or helium? Do what? Set fire to it? Oh my gosh. You're a crazy crowd. What is it with you Egyptians? Anyway, that is a good idea scientifically, because you may know that helium doesn't burn. Hydrogen, on the other hand, is very flammable, very dangerous. So I suppose if I tried to set it on fire, I could find out whether it was hydrogen or helium. So let's just light a match here on the end of a stick so I can reach it up there. And let's see if it sets it on fire. Well, it popped the balloon, as you might have suspected, but it didn't set it on fire. Now, would you like to see me do it again? I have another balloon. Okay, so we'll light this balloon. And you see my assistant Ahmed with his fingers in his ears? If loud noises bother you, you may want to do the same, just in case it's not helium. Okay, so that indeed was hydrogen. And you probably have heard of a large balloon that went across the ocean called the Hindenburg in the 1920s, I think. And it caught on fire and it killed a lot of people. So they don't put hydrogen in balloons anymore on a large scale because it's potentially quite dangerous. But there are other things we can do with balloons. I'm going to fill another balloon with helium. So here we have a tank of this helium that we used before. And we're going to put some helium in this balloon. And I'm going to do something maybe you've seen someone do before, and maybe you've even done it yourself. What I'm going to do is breathe the helium. Now, I want to caution you. Most gases you breathe are harmful. Don't breathe gases. Even some of the air we breathe isn't very healthy for us these days. But this is safe because this is high purity helium, research grade helium. The helium you get maybe at the zoo or the circus when they're selling you balloons is not very pure. And so it's not a good idea to do this with the helium that you normally encounter. But we can do it safely here because this is high purity. And you may know that deep sea divers sometimes breathe an atmosphere of helium. So it's quite safe as long as it's pure. So I'm going to breathe it and we'll see what it does.
And as you see, it makes me talk a little bit funny. It makes me sound like Donald Duck. Do you know Donald Duck? He's a